Hi, this is Zhenggong, and our work is the NeRFDeformer, the NeRF transformation from a single wheel with 3D sync flows. In this work, we are interested in automatically transforming a NeRF given a single observation showing a non-rigidly transformed version of the original NeRF capture scene. Here it is our task definition. Given a NeRF of the original scene, which is trained from multiple views of that scene, and a single RGBD image of the transformed scene, we are interested in producing novel views and exporting the mesh of the transformed scene. Now we will show how the scene is re-rendered given a new camera pose in the transformed scene and how we generate the transformed scene mesh. At its core, our method recovers both the 3D scene flows, a forward flow A to B and a backward flow B to A to link the original scene A and the transformed scene B. To render novel views of the transformed scene B, we sample points viewed along the ray in the transformed scene and apply the backward 3D scene flow FB to A to obtain the corresponding points. Then these transformed points are then fed to the original NeRF-based rendering. And similarly, the original mesh is obtained from the NeRF of the original scene with the classical merging cubes algorithms. And the transformed mesh is then obtained by applying the forward flow to all the original vertices. Now let's move to details about how two flows are defined. We model both flows as embedded deformation graph. We first introduce the forward flow, which maps an arbitrary location PA from the original space A to location PB in the transformed space B. We first have rigid transformations denoted as chi anchored on mesh vertices. We show them as green dots here. Now we are computing the weight of these rigid transformations. It's based on k nearest the neighbor search, and here k is 3. The nearer higher the weight is, and all anchor points farther than the third nearest points has a 0 weight. The final transformation is formatted as a weighted linear blending of rigid transformations. For the backward flow mapping from space B to A, we can extract that directly from the forward flow. First, we naively inverse the rigid transformations used before. Then we anchor these transformations to vertices of the transformed mesh, and the weights are queried among them. Finally, the transformation is a similar weighted sum of inverse rigid transformations. We now discuss how to find and parameterize the flow. The only learnable parameters are the rotation and translation of rigid transformations. Here are two parts of the whole loss, the as rigid as possible loss and the consistency loss. We use the atom to optimize. The as rigid as possible loss encourages local rigidity of the transformation given the connectivity of the anchored vertices. Please check the original and our paper for more details. And the consistency loss constrains the translations of the corresponding points between the original and transformed space. We use the mesh topology for vertices connectivity. Now let's discuss how to get corresponding point set. We first find 2D correspondences between the transformed RGB view and original NeRF-produced renders, then filter in pixel space. Then we lift the pixel correspondences to 3D and filter the false positives in 3D space. For more details, please check our supplemental video. Now let's move to our results. First, for the quantitative results, we significantly outperform the other baselines in both new resynthesis and geometric reconstruction. Especially, our PSNR is 3 higher than the second best baseline, but the chamfer distance is 4 times smaller than the second best one. Then for the qualitative results, we first show the training and transformed views in the first column, then new view synthesis of ground truth, Dream Gaussian, Sine, and our method in the second and third column. Finally, the transformed mesh of the 4 in the fourth column. We can see that our method always has clear new view synthesis and geometry reconstruction, where all other baselines struggles for that. And here are more results. Thank you for listening.